professors.
Okay.
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 Get started. All right. So we are very happy to have Doug Tuckler here, who's visiting us from TRIUMF, and Simon Fraser. Doug was Stefania's student at Santa Cruz and then went to Carleton and has now moved to the other side of Canada.
Yeah. And
he's going to be telling us about dark sectors at lepton beam dump experiments. So take it away.
Yeah, awesome. Yeah, thank you so much, Rob, for the invitation. It's nice to be here. So first time I've been in Minnesota ever. It's quite nice. It's nice to be in the Midwest also. So like Rob said, my name is Douglas. I'm a postdoc at TRIUMF and Simon Fraser, and I'll tell you about looking for dark sectors at future like electron machines, high energy electron machines, in particular, prospects or ideas for putting beam dump experiments at these machines in the future. So since this is somewhat of a dark matter talk, I need to okay, 1 second. Since this is a dark matter talk, I'm legally obligated to give you a slide about why we know dark matter exists, and there's a lot of evidence for it, right? We have galaxy rotation curves, just sort of the thing you always hear about, gravitational lensing in terms of bullet clusters and in terms of the bullet clusters like this. The CMB tells us that dark matter has to exist, and we also know from the abundance of primordial elements that not all of the stuff around us is made up of just ordinary matter. There's the energy density of stuff is also includes dark matter. But all these observations tell us about the macroscopic properties of dark matter, how it interacts gravitationally, and what we would like to do is try to figure out what are the microscopic properties of dark matter, if it has any, which we hope that it does. This is a hard question to answer because the mass range of dark matter is extremely huge. It's like 90 orders of magnitude in mass, and you can try to place your dark matter candidate here, and there's a whole, there's a large number of theories that give you any dark matter candidate. So how can we possibly hope to probe this entire parameter space, or what are the best targets that we can look for in this parameter space for dark matter mass? And one guiding principle is to assume in the early universe that dark matter was in thermal equilibrium with the standard model, bath. And this simple guiding principle narrows down your parameter space from like 90 orders of magnitude to something like 6 or 8 orders of magnitude, from about a keV to 100 TeV. And it's actually a bit more restrictive than this because you can't have, if your dark matter is too light, it'll mess up BPN. So you have to have dark matter that's above about an MeV in mass and sort of less than 100 TeV. And so this is your thermal dark matter range. And so this is a good target to go look for. And these are the two typical, the paradigms that we think about, sort of the WIMP dark matter and then this light dark matter regime, which is below about a GeV. And this traditional idea of WIMPs, of weakly interacting massive particles, there's a lot of efforts to look for this in the past few decades, especially in direct detection experiments. And what I'm showing here is just the parameter space of your spin-independent dark matter scattering cross-section with the proton nuclei in your detector and the mass of this dark matter candidate. And you see that this is a bit outdated analysis from a few years ago, but already the experiments are starting to really probe deep into this parameter space of WIMP dark matter. And already in the future, we'll start to reach the neutrino floor, where you have to think about new ideas to how to mitigate that background, because using maybe directional information about the dark matter compared to neutrinos or something like that. So this is starting to be, I guess, in the past decade or so, ideas to go beyond the WIMP paradigm have become really, really popular. And there are two ways, I guess, to try to additionally go beyond this parameter space. I think one way, of course, is to go weaker, but this is difficult because you run into the neutrino floor, and it's really hard to distinguish dark matter from neutrinos in this parameter space for WIMPs. The other option is to go lighter. You see that these direct detection experiments lose sensitivity at lower masses, and so there's a lot of parameters that's open to try to play around in this sort of sub-GeV range for dark matter models. Beyond the WIMP paradigm. And in these models, these light dark matter models below GeV are interesting because if you have light dark matter, you also need some additional lightning particles to mediate the annihilation in the early universe of these dark matter candidates and standard model stuff. If you just have interactions of dark matter with Z bosons, for example, or things that are electroweak particles, they're heavy, you have some bound about a GeV or 2 GeV that you can't go below. So you need new stuff there that's also light. Because these things are light, they have to be standard model singlets. Otherwise, you would have seen them at colliders already. So because they're singlets, this gives rise to these sort of portal models Or you have a dark sector where the dark matter is part of, it has its own new dynamics, some new particles. And then you have these singlets that are mediators to the visible sector. And so some of the popular portal models that people talk about are dark photons. So just a photon with some mass that mixes with the standard model photon. You have a dark Higgs and some heavy neutrino portals as well. And these new portal models come with their own rich phenomenology that you can look for in experiments. As far as experimental searches go, you can these portal models typically have really like small couplings, and so you give rise to long-lived particles, which is also a challenge to search for in current experiments. Sure, in terms of actually looking for these things in the schematic of the coupling versus the mediator mass. So here are the current bounds from things like the LHC or previous beam lump experiments. And this is where these long-lived particles live. And if you want to probe this parameter space, you can do two things. One, you can go higher in energy, so you could probe higher mass things, which is sort of the goal of the LHC and maybe post-LHC if we build a higher energy collider. The other option is to try to really probe down into these feeble couplings by having a very intense, a high intensity experiment. So you produce a lot of these particles, and so you can get around having really small couplings. But ideally, what we would like to do is try to go in both directions. Go to high energy to probe higher masses, but also go to high intensity to probe these small couplings for these feebly interacting particles, elongative particles. And to go in, I guess, as far as intensity goes, I think beam dump experiments are really the most promising avenue for this, because you have a very high intense proton beam, something like 10 to the 20, 10 to the 20, 10 to the 19 protons on target. So you can produce a lot of dark set, these long-lived particles. And in this schematic, I'm showing just an example for heavy neutral leptons, which are produced from meson decays. But these things are produced a lot from meson decays, and they travel a long distance, and then they decay far away. And some detector, and you can put some decay volume, you can put a detector far away and try to look for some charged particles that this HNO has decayed into. But yeah, so these are just some examples of current proposed and proton beam experiments. So something like SHIP, which has sort of 400 GeV energy and 10 to 19 protons on target per year. And things like DarkQuest and Dune as well are good proton beam dump experiments to probe dark sectors. But you have this large flux of protons hitting your target. So you have a large production rate of dark sector particles. I just want to know one thing, that the DarkQuest recently received some like R&D funding to be built, I guess, in, I don't know, 5 to 10 years, maybe, I think, which is really exciting. But the SHIP experiment, I've been hearing about the SHIP experiment since I was in graduate school, and everyone talked about like, this is like the ultimate experiment to try to look for dark sector particles. And it's a dedicated experiment to look for dark sector particles at the LHC. So you use this high intensity proton beam from the SPS at the LHC to produce a lot of dark sector particles. It's 400 GeV in energy beam. And a lot of work in the past decade has gone into understanding all your backgrounds, meson production, muon production, maybe say how to look for neutrinos, how to look for dark matter. A lot of work has been done for SHIP, so that you can actually look for long-lived particles and these dark sector particles in the future. But despite all that work, we don't know if SHIP is going to get built. So before I get to that, all these studies at the end show that the SHIP sensitivity for new dark sector, the SHIP basically beats everything in terms of dark sector particles. So here I'm just showing a plot for a dark photon portal model from Rob's nice review from the SNOMAS process last year. And you see that SHIP basically is sort of dominating above anything else for the dark photon portal model. For Higgs portal, SHIP also does pretty well. I mean, Methuselah can do a bit better, but at these higher masses, SHIP is the one that's sort of can lead the sensitivity there. And even for these heavy neutral leptons, this heavy neutrino portal, SHIP is also kind of again leading compared to all the other proposed or existing experiments. Because energy and then the flux, yeah. Yeah, so I think 400 GeV is good. It's like a middle ground between high and low energy, so you can produce heavier things there. But beyond something like DarkQuest or Phaser, well, Phaser you can produce heavier things, but they lose because of geometric acceptance. But for things like DarkQuest, which has like 100 GeV beam, it's harder to produce heavier things. So SHIP is like really in like a sweet spot of energy charge, produce heavy, like sort of heavier than GeV things, but also has a large flux, which is really good. That's a good question. I don't know. I think they're doing some R&D funding, research, like small scale stuff, but I'm not entirely sure.
So just to be clear, you said you're thinking about the case where dark matter interacts through some mediator with the visible
Yes.
and you're mostly looking at the mediator here?
Yeah, that's right.
Okay, so you started off the talk by saying that the like motivated mass change for dark matter is half of the mediator.
Yeah.
Is there a reason why I should expect the mediator to be in that mass range? Like, why are you looking in that mass range?
So if you want thermal dark matter in the early universe to annihilate, the cross section goes as one over the mass of your mediator. And so if you have something that's really light, you can enhance your annihilation cross section, even though you have these small couplings, these feeble couplings for dark matter. So you need light stuff to get the correct relic abundance.
This is the Lee Weinberg.
Yeah.
To have a thermal story below,
Yeah.
you are required to have. You're required to start that flight.
Oh, because the mediator.
No,
No,
just to get the right, like, just to have freeze out.
Yeah.
You can't have freeze out of, let's say, like 10 MeV dark matter through like electroweak scale mediators. So you start like without running.
Yeah.
So you just have to. And if your mediators are. So generically for sub UV stuff, you immediately start thinking, for sub UV dark matter, you immediately also start.
I guess you don't want to.
Yeah, not too like, this is
Like in
GV with 10.
Yeah.
I'm just saying how
Yeah, lighter than that, you're gonna run to ineffective first. Like,
Yeah.
Right.
Yeah.
So this is the sweet spot.
Yeah, that's right.
And here is the meat.
This is the mediator, right? Yeah, so the mediator, so the assumption here is that the dark matter is heavier than your mediator. So the mediator has to decay visibly rather than to dark matter. And so this is sort of so that currently with all the future and current bounds on these kind of models, but this is just to show that chip is sort of the best option to try to freeze dark sector particles. So it'll couple to the Higgs and to you can couple so it'll couple to the Higgs and to like a neutrino, but you can also couple the neutrino to some dark sector particle via like some other dark Higgs. You could add some other extra interactions. Okay, so that's the status of these searches right now. But then the question is SHIP ever going to get built? And I was talking to David Morrissey last week, and he said this. I thought he said this like interesting thing that NA62 took the wind out of SHIP. This additional this one.
One that's coupled.
Yeah. So this right-handed. This is just a right-handed neutrino. It is a right-handed neutrino, just GeV scale. It can participate in generating neutrino masses like standard seesaw mechanism. I'll show a slide about it in a while, in a little bit. Yeah, that's right. But that's if you have one right-handed neutrino. If you have more than that, then you can get away from it.
We're doing more season on that.
You have a tiny mitochondrial mass for wolfram, tiny coupling.
Season all very.
But okay, so yeah, we don't know if SHIP is going to get built because there's an experiment that already exists at the LAT called NA62, or it's called NA62, which also uses a 400 GeV beam, and it can be run in proton beam dump mode. But it's meant to look for rare K, like K on decays, but It's still a similar or a roughly similar intensity as SHIP, 10 to the 18 protons on target for 3 months, and the sensitivity for Na62 is somewhere in the ballpark of what SHIP can do. So if we already have Na62, then why do we need SHIP? It's a question that can be asked. For SHIP? That's a good question. I think there's a proposal to put SHIP in, I think in the same facility as Na62, as like some other FARA to, the same hall,
It's like.
There's like 4 proposals to put different beamed up experiments in that hall. Yeah. I think Shadows is the name of one of them. There's another, anyway. So anyway, the point is we don't know if SHIP is going to get built, and Na62 can basically do some of the things that we expect, maybe want SHIP to do. So why spend money on SHIP? It's an expensive experiment, even though it's good. So there are alternatives to SHIP. I already talked about DarkQuest. Here I'm just showing again, see the bounce from dark photons for these dark photon portal models, and the table again for SHIP, DarkQuest, and Muon in terms of the intensity and the energies. And so DarkQuest is kind of low energy, well, in quotation marks. I mean, so you're not able to probe very heavy things, so above a GeV. And you have a sort of a lower intensity, which is not good in terms of production of these things. But it's still so, Dune still kind of probes interesting parameters for dark photons. Dune, on the other hand, it's a similar 100 GeV electron proton beam on some target, but it has a very higher intensity than DarkQuest or Dune. So 10 to the 21 protons on target per year, and it can cover a substantial region of parameters, especially because like the near detector for Dune is pretty far away, so you can go into more feeble couplings. But I also don't know when Dune is going to start running or what the status of it is, and so Phaser is already running, which is nice. It's at the LHC. It has high energy proton collisions to produce a lot of mesons, which then decay to dark sector particles, or you produce dark photons via proton bremshelling and so on. But the problem with Phaser is that even though there's high energy, it's a very, very far detector, and you lose a lot in geometric acceptance because you produce dark sector particles sort of isotropically in all directions, and you only pick out a tiny region in angular acceptance. So this gray curve here is like the recent Phaser result for dark photon searches from last year, which is cool. You might ask, well, what about putting a proton beam dump like at the LHC, using the TV protons, hitting some dump, and then putting a detector behind it? The problem is that the proton beams, they circulate, so you can't dump them every single time it goes around. So you dump them a few times a day. And if you run for 1 year, you find that you get something like 10 to the 17 protons on target per year, which is not a very high flux for producing dark sector particles. So it's a very low flux. And so it's not so good for FIPS or for long-lived particles. And there was this proposal to put a neutrino detector behind the LHC beam dump was made by Kevin Kelly and company in 2021. And they said that, this isn't so good for dark sectors, which is unfortunate. But now the question that I want to get to is like, what if you change the proton beam into an electron beam? And so let's think about electron beam experiments. And so here I'm showing, again, a table from the SNOMAS report, the RS6 SNOMAS report, and I've highlighted in purple all the future electron fixed target or beam dump experiments. And you stare really closely, you see that the energy of all these things are sort of about a GeV to 10 GeV, except for the Na64. So it has a 100 GeV electron beam or 100 GeV muon beam. And Na64 has done a lot of, has a lot of good results, especially recently they had a Na64 mu ran, and they had some searches for like some mu-minus delta gauge boson, and they said something about the anomalous, the G-2 of the muon and so on. But besides Na62, NX64, right, how do we go higher in energy to try to probe heavier things, and how do we go to higher intensity compared to what we currently up to these experiments here? And there are proposals one way there's proposals in the future to build, precision Higgs factories, E plus E minus machines, for the International Linear Collider. There's this recent cool copper collider that's sort of supposed to be a US-based E plus E minus machine. Click obviously is also a future experiment. So these have higher energy electrons, 250 GeV electron, 125 GeV electron beam, 500 GeV electron beams, and so on. TV electron beams. So why not build a dark sector facility at some future E plus E minus machine to study long-lived particle dark sector, and just try to design a beam dump at these experiments or maybe some far detectors, to study dark sector particles. Why not just do that as part of the plan of these future facilities? And there's some advantages of using these electron colliders. Again, they're high energy, so you have hundreds to TeV of energy beams compared to past experiments or compared to some proton beam experiments. On top of that, there's a stage energy approach. I mean, you start at 125 of 250 GeV center mass energy, so you do some Higgs physics, and over the years you kind of increase your energy in the staged approach, and this is nice to probe higher dark sector particles. Because you don't need to build a new higher energy facility every single time you want to change your energy to look for higher energy to probe heavier things, which is nice. The high intensity, so there's 10 to 21 electrons on target at ILC if you calculate what that is. So just for 1 year of running, that's that thing that's 2 orders of magnitude larger than what you do at ship. And because you have some electron-proton collisions, you can have some additional new production modes for dark sector particles. For having neutral leptons, for example, that coupled to the electron, that mixed with electron neutrino, you have charge current scattering of the electron with your proton to produce directly the heavy neutral lepton rather than going through meson decays. Or if you use the positron beam, you can have pair annihilation to produce dark protons or ALPS. I think another advantage of this is that to put new detectors at the experiment at the LHC, you have to either find some cavern or some hall that isn't being used. So you have to try to find that space at the LHC, which is a bit difficult. Here, the advantage is that we haven't built a E plus E minus machine, so we can start to think of how to include this as part of the design of these machines in the future. And so these are the 3 experiments I'll focus on: ILC, CQ, and click. And here's just sort of the center of mass energies. And then the electrons on target per year. So ILC is 4.1 times 10 to 21 times 10 to 21, and a CQ then click running at this 3 TeV is similar 1.8 times 10 to 21. So I'll focus on these. So ILC 350 and 1000, and then CQ then 60,000.
So very nice question.
Yes.
Being a collider, yes, but do people usually think about the beams after the beam pass each other? Some particles of the beam will not collide with each other.
Right.
If they stack up, then you just stack it.
Yeah. Yeah, they'll pass by each other, and then you have to dump them anyway.
So in a sense,
Yeah, you have to dump them anyway. So just put a detector behind it to make use of this dump, and why not? And then because you don't have to recirculate them, you can just get a lot of intensity or a lot of electrons on target. Yeah, exactly. That's like the main take-home message of my talk. Thank you. So we'll use, this is the electron beam dump setup I have in mind. Some electron beam hits a water dump, which is 10 meters in length. Then you have a 70-meter muon shield made of lead and concrete. This is just to kind of absorb all the muons that you produce, which kind of punch these things a lot. You could imagine putting like maybe some magnets to kind of also deflect those muons so you can lower your backgrounds. And then you have a decay volume that's 50 meters. And at the very end, you put a cylindrical detector that's 2 meters in radius. And cylindrical, it just makes things a bit simpler in terms of calculating sensitivities. So this is the setup I have in mind. And the case study is heavy neutral leptons. So this is stuff I worked on a couple of years ago with Stefania Gori and her grad student, Pierce Gifton at UC Santa Cruz. These are just standard model singlets they introduce to give neutrinos masses. So here's the Lagrangian for that. You have some Yukawa coupling of the Higgs and the right-handed neutrino. You have a Majorana mass term for the right-handed neutrinos, and then you do electric symmetry breaking. You generate a Dirac mass, you generate a Majorana mass for the right-handed neutrinos. The Dirac mass of the standard model neutrinos is proportional to this Yukawa coupling. And so, you were mentioning that if you want to get the correct neutrino masses, this has to be kind of really small, but that's only if you have, having one right-handed neutrino. You can get away from it if you have more than one. But since this is so then after this, so once the neutrinos and the right-handed neutrinos and the standard model neutrinos mix, then the right-handed neutrino just has all the same interactions of the standard model neutrino, just weighted by some mixing angle, I'll let you alpha. Well, alpha denotes the flavor of whether you mix, which neutrino you mix with the electron, the muon, or the tau neutrino. So any place where you produce a neutrino, you can also produce this right-handed neutrino, and you can try to search for it in detectors. And so for this study, we take sort of the pheno approach, where we assume there's a single flavor that the right-handed neutrino mixes with. So I'll focus on electron mixed right-handed neutrinos, and then muon and tau in the future. Sorry for the what do you mean? I guess, yeah, if you take mn to 0, you probably couldn't take mn to 0. I think you'd run into, I guess if they're produced in the early universe, you run into something like too much radiation, right? So delta N effective might affect that, but yeah, I don't know. That's oh, yeah, I mean, yeah, certainly you can do that. Yeah, certainly you can do that. I mean, but you have to. Yeah. Okay. Yeah, but yeah, I don't know the answer, but yeah. Yeah, all right. Yes, but yeah.
You probably should switch it. Now motivated.
Yeah, I agree. But this is just sort of some pheno analysis, so we do kind of the pheno thing and just say, but just one neutrino, let's see what we can do. But yeah, that you're right. Yeah, so for muon, these electron beam up experiments, for the electron mixed HNL, you can produce it through meson decays, or through this directly through charge current scattering of the electron with the proton. So I'm showing the production rates on the left for meson decays, and the right for charge current production for this mixing angle 10 to the -6. And you see that you have in 1 year of running these experiments, you have a fairly large flux or production rate of these heavy neutral, these right-handed neutrinos from meson decay. And yeah, and similarly from charge current scattering. But the thing to know is that above the d meson mass, so if where these green curves end, so b meson, you produce order 10 to the 4 of these HNLs per year. But from charge current scattering, you get something like 10 to the 5 HNLs per year. So above the d meson mass, this is the main production mode for these HNLs, which is another advantage of having electron beam dump experiments. In terms of, so once you produce them in meson decays, these things travel, they'll decay. And here I'm just showing the different decay modes and the branching ratios for the electron mixed on the left and the muon mixed HNL on the right. And what we want to look for 2 charged particles in the final state. So for electron mix, some electron and a pion, or an electron and a muon, or the 2 electrons, which helps at lower masses. And for the muons, it's sort of the same. A muon and a pion, look for E mu, and then maybe E, which shows up at lower masses. And then you put this stuff together, you try to figure out your production rate, your decay rate, you take into account geometric acceptances, the probability of your HNL decaying in your decay volume. And this is these are the constraints you get, or the sensitivity you get for at these different electron beam dump experiments for this electron mixed HNL. And so the different terms are for the different energy stages. So 250, 1,000, and 3 TeV, 1 TeV and 3 TeV. And there's some complementarity between this ILC, these beam up experiments, and sort of existing proposed experiments like Phaser, Codex, and N62, and some of these existing bounds. It doesn't go all the way to sort of the ship bound or Methuselah, which is unfortunate, but there's some complementarity, and especially at higher masses. And up here is where the charge current scattering kicks in. And you see that you really start to probe parameter space that's similar to Phaser, which exists, and parameter space is complementary to what HLLXC is expected to probe, and which is nice. And this again shows the importance of going to higher energy, which lets you probe deeper and deeper into higher, which is nice. For the muon and the tau mixed HNLs, it's a similar story, some complementary reach for meson decays for the muon, and then for the tau mixed HNL from B mesons, you get something can go to higher masses. Production of HNLs would be that. So that's kind of nice. There's complementarity, ILC beam experiments, and existing experiments. And in terms of the muon mixed and the tau mixed HNLs, maybe you, in the far future, you have some muon beam dump experiment to do charge current scattering of muon with some beam dump to maybe probe this parameter space. Maybe infinitely far away, you have a tau beam dump experiment, and maybe.
Go back to the background.
Yes.
To cover any new having the which is going to happen.
Yeah, so there's a very tiny window here, like between 2 and 3 GB that probes some new parameter space. Yeah, so yeah, it's just a proof of principle that you know these experiments are also good for dark sector searches compared to, I mean, in the absence of SHIP, for example. Yeah. That's a good question. There should be a line somewhere down here, but I don't have it on here.
Like is vanilla seesaw anywhere on where?
Yeah, I don't know exactly where it is. I don't know if it's below 10 to the 10 or somewhere in between here. I forget exactly where it is, but yeah, it's not on there. I could add it if you want.
Well, I'm just kidding. Like, it's outside this block.
Yeah.
Yeah, I think it's
Yeah, that's right. Yeah, so it's down here.
But it's like all right. Yeah.
Yeah.
Force is on top of it. Back even for turn on all three flavor mixing and to scan all the parameter space, you can also populate.
Yeah, that's right.
So even normal seesaw is all three mixing with multiple generations. It's almost 100%.
Yeah.
Like the two additional actually form super. But it is a TRIUMF.
Yeah, that's right.
So examples, it is motivated by stuff. Simply isn't working about that.
Yeah. Okay. Yeah, beyond the heavy neutral lepton, there's some other benchmark models where the IOC does really well. So on the left, I'm showing dark photons, and on the right, I'm showing photon coupled ALPS. So these are some studies some in the past couple of years by some. I just added them to this plot and showed where this beam dump experiment is compared to other experiments. And so for dark photons, an ILC beam dump experiment, because it has a much longer decay length, decay volume, it sort of beats a dark quest by about an order of magnitude, which is really nice. And then at the higher mass is sort of similar. And then for the photon coupled ALPS, right, this ILC beam dump experiment even actually beats SHIP, although I don't know the details of the SHIP study, which exactly what signature they're looking for there. But it beats SHIP, it beats dark quest. Dune will do as well as ILC beam dump experiment, but in the absence of SHIP, these ILC beam dump experiments can have better sensitivity to these dark sector models compared to dark quest or phaser. So it's worth trying to think about putting a beam dump experiment at these machines because they're just because of the high intensity and higher energies. Okay, and then I think, yeah, so that's my first take-home message is that we should think about building a beam dump experiment at plus minus machines because of the high energies, because of the high intensities, and we can start thinking about implementing this as part of the entire design of a future E plus E minus machine rather than finding some cavern or some hall like the LHC. Yeah, so yeah, and they're very complementary to existing searches or future searches for these start part of it. So any more questions so far? Yes. I don't know. I don't know the answer. I mean, ILC, yeah, people have been talking about ILC for a very long time. But in the past like 5 or 6 years, this cool copper collider, the C-cube thing is so the basic idea that I only know that the way to design the accelerators, they use some copper cooling technology, which allows you to have higher like RF gradients in your linear, but you can make it smaller. So you reduce your cost of making your linear accelerator smaller, but you still have higher energies or same energies ILC, just cheaper. It's just some new technology that's been popularized. I think there's proposals to make this in the US. I think there's a proposal to build it at Fermilab, but I don't know, how feasible that is, or There's also proposals to say, instead of like picking CQ versus IOC, let's just, if IOC gets approved, let's try to use this cool copper collider technology to make IOC, better in a sense. But I don't know which when, or CQ wasn't on P5. Okay. Yeah, that's tough. Yeah, unfortunate. Okay, so there was one thing that was on P5, and that was Muon Colliders. So now let me basically think about Muon Colliders. So there was a talk a few weeks ago by Carrie says earlier here. She talked about Muon Colliders, all the technical aspects about this, the challenges, and what you can do. But Muon Colliders are great because muons are fundamental particles compared to protons. So they take all the center mass energy to produce, rather than having some part of the proton to try to produce some particles. And because of that, you see this plot very often that tells you that a 100 TeV proton collider is similar to about a 10 or 15 TeV muon machine. So, which is pretty cool. There's also, compared to electron machines, you don't have a lot of issues with like Bremsstrahlung off of the muon because the probability of emitting a photon that goes as 1 over the mass. So you have less emission of photons, so you have to think about having sort of super strong magnets to try to bend your electron without it losing so much energy and things like that. So, and then the physics potential is typically you think about Higgs physics, vectoric physics, physics associated to vector boson fusion, or very heavy dark production, production of heavy new physics. And so here's just some thoughts from one of the Muon Collider papers, which I've linked up there, showing the reach of the Muon Collider to say some Higgsinos or Winos, and so some Higgs portal stuff, which is so it's complementary in terms of a high energy machine. It's complementary to other proposals like IOC, click, FTC, and so on. But yeah, so can we use this Muon Collider also as an opportunity to try to maximize the physics potential by also building maybe auxiliary detectors at a Muon Collider, such like a beam dump experiment as well. And so another nice thing about Muon Colliders is just sort of not a mature technology. There's a lot of technical challenges. There are going to be a lot of different stages where you try to demonstrate that the technology works, starting from sort of low energy and slowly building up to higher energy. At each stage of these studies, we can put a beam dump experiment there and try to produce dark detector particles at each of these stages. So we don't have to wait until the full-fledged Muon Collider with the high energy, the highest energy that we want to try to start probing dark detector particles. We can already think about putting a beam dump experiment there and try to look for dark detectors along with particles. And so here, the beam dump, the scenario that I have in mind is just exactly the same setup as a IOC beam dump experiment. You have this 10-meter beam dump, this 7-meter shield, 70-meter shield, some 50-meter decay volume, and so on. This is different from some of the studies that have been done by Carey and Cesarotti and others. So they have very different beam dump setup. But for simplicity and its comparison directly with IOC, I just chose these things, just replacing the electron beam. And again, we can use heavy neutral leptons as a case study. And here I'm just showing some different production decay modes. So from kaons, from D mesons, and from B mesons. And so the solid colored curves are for this muon beam dump experiment with the muon beam energy of 500 GeV. So it's called mu BD 1000. And then the dashes compared to IOC. And you see that you have a lower production rate of meson of these dark detector of HNLs compared to the IOC. And I think the reason because of this is, again, because the way you produce mesons in an electron beam dump, in electron proton collisions, you have to exchange a photon you have to get a photon from the electron and a gluon or a quark from the proton. And the probability of emitting a photon from the muon is a bit low. It's lower than an electron. So naturally you have a lower production rate of mesons. I think this is the reason why this is the case. I have to look into this more, but I think that's the reason why the sensitivities are you have a lower production of mesons and therefore a lower production of heavy neutral leptons. But it's somewhat complementary, and if I put everything together, all the different searches, existing searches and dark west phasor ship. So for a muon beam dump experiment, you gain compared to you still gain a little bit from B meson decays compared to it's a similar story as before. You gain a little bit of meson decay, but not like a lot. But that's a meson decay case. And it's still complementary dark resonant phasor, and then you have reach beyond the D-meson mass, which is nice. But then the cool thing is now you can have charge current scattering of a production of a muon mixed HNO. And this goes exactly the same as the electron case, same cross sections, so on and so so you run your analysis, you do geometric sentence, production, decay, and so on. And these are the three different curves. If you assume the same energy stages as the electron machines, and here you're really starting to go beyond what HLOHC can do, and even to higher masses, beyond 10 GeV for HNOs. And this is really new parameter, really good complementary probe compared to the high luminosity LHC, above the D-meson mass or above the B-meson mass even. So this is pretty cool. So this is very preliminary, but I think this is an interesting result to try to put a muon beam up experiment just to do charge current scattering, direct production of an HNO. So I use same as ILC, so I assume 10 to the 21 muons on target per year. I don't know how feasible for 1 year. Yeah, I don't know how feasible that is or technologically, but yeah, might be very, very optimistic, but it's still so this is pretty nice. You saw some complementarity, and it's interesting to think about this. And again, you can also look for dark photons at these machines. So here, I've added the muon beam dump curve for this 1.5 TeV electron beam, and this is from Kerry Cesaroti's paper from a few months ago, from last year. They have a very different beam dump setup. They use a lead target. They have a shorter shield, a shorter target, and like a longer decay length. So at the end of the day, it's still complementary to Dark Quest and Dune and even ILC. And the advantage of having higher energy to go to higher dark photon masses is still important here. So that's the muon beam themselves. So that's just takeaway number 2. Just muon colliders are another promising approach to look for new physics, take precision, heavy new physics at TeV scale. But we can also use it to look for dark sectors. I mean, why not? It hasn't been built yet. Let's try to design something to look for dark sectors with high intensity muon beam, and try to probe some of these interesting portal models. And so that's the takeaway number 2. And all the technical details about or challenges about how to do this, you can see Harry's recent talk, which is a YouTube video, which is pretty cool. Yeah, any other? Yes.
For both the electron and muon cases, you made this argument that if we already had the beam, then all we need to set up how easy is that actually? For Atlas and CMS, I'm under the impression that these detectors are pretty complicated. Is building the detector actually much easier than making the beam, or are they both?
I mean, I think you just need something that's look for charged particles, right? Some some spectrometer that's similar to SHIP, right? You don't need to build some huge 4 pi thing like Atlas or CMS, right? It's just put something far away. It can measure muons, electrons, photons very well.
Okay, like a beam dump detector is much simpler. Or at least you could do stuff.
Yeah, I think a simple detector you can useful stuff. Yeah.
Okay. Oh, because you only want.
Yeah, everything's produced in the forward direction, so you only care about putting something in the forward direction far away. And okay, any other questions so far?
So for ILC, it's reasonable to assume the dump.
Yeah.
Actually, the dark
Yeah, that's right. So it's a question about whether you do a circular collider or not, right? Like if the muon colliders it's going to be a circular collider, I expect. So you wouldn't dump it every single time. So I think this 10 to the 21 muons on target is a bit optimistic. Like that.
You have to dump it.
goes around a few times.
So I keep on injecting, right? Those decay in flat, they decay in flat. Quite a bit. If dynamics become unstable, that's the time scale I said.
Yeah, regardless, I think it's optimistic, but it's fun to think about putting a muon, having a muon beam dump experiment. Okay, so I have, how much more time do I have? 10 minutes?
Yeah, easy.
Okay, perfect. Then I'll move on to the last thing I want to talk about. And this is sort of a shameless, well, half shameless ambulance chasing. And so I want to motivating putting a Higgs position, some Higgs position machine like the E plus E minus machine from indirect indirect dark sector searches. And this is, yeah, the ambulance is a recent Bell 2 result, and we kind of an idiot phenomenologist trying to see what you can do with this. So yeah, so Bell 2 recently measured B plus to K plus nu for the first time. They use two different methods. One is sort of a standard hadronic tag where you have E plus E minus goes to a B meson and an anti-B meson. The anti-B decays into hadronically, and so you can tag it. And then on the other side, you look for a very high energy or of a kaon with high PT, and you try to reconstruct your B meson that decays into the K plus using that information. The other way they look for this is this inclusive tag, where you have your signal B meson decaying to a kaon, so you look for a high PT kaon. And then on the other side, you have your B meson decaying to everything that it possibly can. And this just improves your signal compared to the other case by, I don't know, I think something like 8% was on the Bell 2 paper. But if you look at their paper, they have these two measurements for the hadronic and inclusive branching rates, something like 10 to the minus 5, 1 times 10 to the minus 5 for the hadronic. And for the inclusive tag, so it's cut off, and I apologize, but it's also 10 to the minus 5. So 2 10 to the minus 5 for the hadronic and inclusive tag. And the standard model prediction is 4 times 10 to the minus 6. And so the inclusive tag is sort of, the hadronic tag is sort of consistent with the standard model prediction on about the 1 sigma level, but this inclusive tag is, has about a 3 sigma tension with the standard model prediction. So you might think, is there a new anomaly in B decays? And so you can try to think about what kind of new physics if you want to explain this with new physics, you can try to come up with some models, some ideas to how you can do this. In order to do this, there are a few things to take into account, right? One, you can take the standard model prediction or the measurement for the inclusive tag and subtract off the standard model, and that'll give you your new physics branching ratio, what it should be to give you this excess. So a few times 10 to the minus 5. So that's your target. The other thing you have to take into account is that things that usually generate B plus to K plus nu will generate B0 to K star 0 nu, and that has not been seen. So there's some complementary there, where if you predict new physics in here, does it also show up here, right? And so you have to be below this bound. And on top of that, Bell 2 gives you this missing mass distribution. So here you see the excess are on, I think it's something like 2 GeV, 2 GeV. The missing mass, and so can your new physics nearly produces missing mass distribution. And the kind of new physics you can think about is the first, you can think about heavy new physics coupled to neutrinos. So you integrate this stuff out, you get some effective Hamiltonian with some left-handed or some right-handed coupling to your quarks. And there have been some studies in the past few months about this. So on the left, I'm showing a plot of where you're allowed to be to explain the B plus to K plus linear excess. And you have to have some non-zero either left or right-handed couplings, which is fine. But the important thing is that, so along this blue curve, if you couple to electron neutrinos and muon neutrinos, we know that lepton flavor universality is a good, holds in the standard model. There were some recent results from the CBE from a couple of years ago that showed that lepton flavor universality is good. And so if you couple to electron or muons, you cannot explain this Bell 2 excess. You have to live in these shaded regions if you want, but if you have lepton universality, you have to live along this blue region. So it's not good. So you have to couple the tau neutrinos. That's one thing. Another study showed that you need a non-zero right-handed coupling to quarks. So this is this purple band in order to explain the Bell 2 excess, the central value of it. And again, here we're showing the interplay between B plus to K plus and B0 to K0 star. from Bell search from a few years ago. So you can do some of it with heavy new physics coupled to neutrinos. That's one idea. You do heavy new physics coupled to light dark matter. And here's you can have some scalar interactions or some heavy scalar interactions, some heavy vector mediators. And here I'm just showing a plot from this paper from the end of last year that shows where you're allowed to live for having some vector mediator. This tells you that your vector mediator has to be sort of at, a few to tens of TeV. And on the right, these are missing mass distributions for different kinds of mediators or different kinds of operators between the quarks and your dark matter. And so having these missing mass distributions can help you distinguish between these models, like which fits the belt 2x is more better and which doesn't. So I think in this case, these green curves, which are vector mediators, tend to peak around where the belt 2x is. But that might be the way to go, which is good. But the thing that I was interested in at the end of last year was, can you do this with light new physics? So if the light new particle has a mass that's below the BMAS on mass, and it's going to be produced on shell, which is a bit challenging because it should appear as a peak in your missing mass distribution. Depending on its mass, it'll show up as a peak. And another challenge is that Babar searched for this process also, and they didn't see anything. And they also provided missing mass distribution. So you have to take that into account. If you want to explain the belt 2 excess, you have to take into account Babar. And that was done by Wolfgang Altmannshofer and his collaborators. And they showed that if you combine belt 2 and Babar, you have to live in this sort of blue shaded region, which tells you that your branching ratio has to be, a few times 10 to the minus 6 for this light new physics. And so this 1.9 times 10 to the minus 5 was sort of the naive estimate of what your new physics should be. But if you take Babar and then this missing mass distribution into account, you get that you want your branching ratio to be 5 times 10 to the minus 6, which slightly lower significance, but still interesting to think about what kind of new physics can explain this. And the simplest thing you can do is just say, okay, I have some light dark Higgs that mixes with the standard model Higgs, so it talks to quarks, and it can be produced in B to S transitions. So we introduced some light dark Higgs. We also introduced some light fermion that's in some dark sector that the dark Higgs can decay to, so it shows up invisibly. And in the parameter space of the mixing angle, sine theta, and the dark Higgs mass, you have to explain the belt 2 excess, you have to live in this blue shaded region. And all these are other constraints from other visible searches of meson decays. But you have to live here. And these different red curves are constraints from invisible decays of the Higgs. So we see that LHC and hydrogenous LHC are not probing the parameter space of this belt 2 excess for the SNC model. But if you build something like the ILC to get much better position on the bounds on the Higgs invisible decay, then you can really test whether this is some light new physics or not. And so we need a new Higgs factory to definitively test this scenario. So it's kind of a indirect motivation for also building ILC or FCCEE, for example, and try to just build a future electron machine to test these dark sector models. Another scenario you can think of is you have instead of having dark fermions, you introduce dark photons, such that the dark Higgs decays dominantly into dark photons, but these dark photons decay visibly. So you have to make sure the dark photons are also long-lived enough so that they escape your detector, the belt 2 detector, before decaying. And if you do that, so we assume sort of 100 MeV or 200 MeV dark photon, and the Higgs decaying again is the Higgs being produced in B plus to K plus, so directly, and then the decays to dark photons, and then you have to live in this parameter space, this blue shaded region. And again, these are again constraints from invisible Higgs decays, and you see that LHC and HLHC are sort of starting to probe the parameter space, but to really definitively test whether this is really new physics or not, you need something like ILC to put better constraints on the Higgs width, if that's the way you want to test it. So it's additional sort of indirect motivation why we should build a E plus E minus machine if you take this excess seriously. Which it's interesting to think about. It was a fun thing to work on with the people at TRIUMF, which is good. This is the take-home message I want to give you. So we have these like future lepton colliders that we're going to build, like the ILCs, the Muon Collider, and we usually think of them as like very high energy machines and energy frontier machines to look for, produce a lot of Higgs and study the Higgs very well, look for, study electroweak physics very well, like top stuff, W boson, Z boson, and to produce heavy new physics at the TeV scale. So this is all sort of the energy frontier. But if we think of what else we can do with these machines, we can also turn them into high intensity machines by putting beam dump machines there, maybe far detectors to look for stronger particles and restudy neutrinos, similar to what Phaser's doing at LHC. And because of this high intensity of these colliders, you can also put dark detectors, which is interesting avenue to really think about to maximize the potential of these future machines, rather than just thinking about standard model stuff. And so there's a lot of synergy that can be done for between high energy and high intensity machines, and high intensity. So I think we should think about building, or think seriously about what else we can do with these machines. So to probe as much as we can, beyond post LHC, for example. So yeah, that's it. Thank you. Yeah.
Is the only thing that matters for the dark photon decaying visibly just for like the red lines that you drew there? Or like, in other words, is the fit for the excess good regardless of it decays visibly?
So it has to decay invisibly, otherwise it would show up in your detector.
Ooh, sorry, you're saying, but the dark photon here, you say decays visibly.
Invisible. It decays visibly, but it's long-lived enough that it leaves the Bell-2 detector before.
Yeah, but why can't it just decay invisibly?
Oh, there's like nothing else for it to decay to. I mean, you can put a dark matter kind of in if you want, but
Yeah, I'm just saying, like, I'm just trying to understand the assumptions. So yeah, for Bell-2, you want it to decay invisibly.
Yeah.
But like for the sensitivity that you're showing at LHC, this is all still just based on like precision Higgs physics, so it doesn't care.
right.
So, okay, so it could decay totally invisibly. You just
Yeah.
as a lower bound to decay.
Yeah. I mean,
Okay.
even for the invisible Higgs cases, right? The amount of Higgs will decay into dark photons also through this mixing. So you have to kind of play around with like the kinetic mixing and sort of to try to get it to actually be invisible. But if it's long enough on the size of like Atlas or CMS or ILC detectors, then it's kind of
The excess that you wanted to increase the branch here with the
Yeah. So if I go back, because the standard model prediction is a level of 10 to the -6, but the measurement is 10 to the -5.
how exactly is this?
It's just additional decay channels of the B meson into invisible stuff.
Of the deep
So it just replaced the 2 neutrinos by dark matter or some dark stuff. It still looks exactly like that, but it's just extra.
You're not seeing.
Yeah, exactly.
But really, when they say a.
Yep. Yeah, exactly.
How come LC can constrain science that?
Oh yeah, I mean, so this is just taking the current measurement of the Higgs invisible decay, and then you compute the branch ratio on this model, which is proportional to the mixing angle. Then you just reverse engineer it and put a bound there.
They're totally different term.
Yeah, I don't know. I mean, I don't understand your question. But...
So I guess you have a party term. Give a dark that for the dark.
I think here we assume that the Higgs here doesn't get a VEV. Oh no, so you can engineer your potential so that there doesn't get a VEV, but it still mixes. It's still gonna mix with the Higgs. No, you're right. Okay, I need to see the Lagrangian in my brain because I can't see it right now, but yeah, I can answer after the talk and pull up the Lagrangian, the potential. Yeah.
That's a silly question. You
Yeah.
showed, I think, way back, we don't have to go back to it, but you showed the sensitivity of, I think, ILC to like alpha photon coupling.
Yeah.
And I imagine people have done this also for like alpha electron coupling, right?
Yeah. There's
Quite good.
do I think I have?
I think you were maybe just showing like a sampling of.
Oh, okay. I thought I had the alpha electron coupling here. Yeah, okay. I thought I had it in a backup slide, but
Yeah.
I don't, so sorry. But
No, no, no. Yeah, like presumably people have done a lot.
yeah. There's all the dark sector stuff for ILC has been sort of fleshed out, I think. Just yeah. Yeah, you're right. We have a like a S H dagger H interaction.
I stagger.
Yeah, we have sorry. Yeah.
Linear.
A trilinear coupling, right? Because S is just singlet,
Yeah,
so it doesn't.
then this coupling induces mixing. It has nothing to do with invisible decay, right? There's no HSS couple. What's your invisible decay? Oh,
Well, once like one Higgs, you give one Higgs of F, and then there's a mixing.
there's a mixing. I said
Yeah.
this induces mixing, but does not induce invisible decay. And I'm asking
Right.
where does your
Right.
horizontal line come from?
Oh yeah. Oh, so we also have like some dark fermion that couples to the scalar, and so that's where the invisible decay comes from. And so we just fix that dark coupling to the one, and then
So really coming from mixing, here is some Yukawa coupling. to
yeah,
the-
that's right.
to
Yeah,
the fermion.
that's right.
Wow, the invisible decay has a lot of dependence
Yeah.
on other parameters.
Yeah, that's right. But
And is there a cross cortic too that contributes or is it
No.
didn't invoke.
yeah, we don't have a quartic coupling. Yeah.
you just have the SH squared and
Yeah.
and then you have this additional stuff that S is.
Yeah.
Okay.
Some dark fermions or dark photons.
I see.
What's the
Which beam?
Yeah, does TRIUMF have a particle beam? It's used to have charming stuff.
Yeah, now they're trying to build up this like electron beam stuff. And so like dark light is gonna be built there to look for light dark sectors.
So what's the energy?
I think the first stage is gonna be something like 30 MeV.
30 MeV
Yeah.
of electron.
Yes. Yeah. Which is
Better to be super high test.
yeah, I have I put on this like table of for the snow mass process. So dark light wasn't on this table, which is kind of annoying. But
Fine, so you're.
so yeah, in addition to the 30 MeV, we still using the 100 MeV after that. I don't know what's gonna get to 100 MeV. I'm having trouble with 30.
What's the kind of luminosity or electrons on 30?
But it's like I don't know, something like that's a good question, but probably low, like I want to say 10 to the something like LDMX probably. I think it's a
It's much lower energy than RDMX.
Yeah.
So what can you achieve?
yeah, that's a good question. That
Oh. So what's its primary physics target?
looking for I think dark matter.
Oh,
Yeah, it's just one of these missing momentum techniques, right? I guess another target for the future, if they get to above 100 MeV energy, is this X17 stuff.
yeah, but that's bullshit.
Is it though?
Yeah, of course. I don't know, maybe. I said stuff without thinking about it.
And maybe it's not.
The elements change the setup, they claim they use their previous